Lecture 9.2, the Biot Savart Law. The Biot Savart Law is an equation describing the magnetic field generated by a constant electric current. Now, I should be a little bit stronger on this. A constant electric current. It is fundamental to magnetostatics, just as Coulomb's law is for electrostatics. When magnetostatics does not apply, the Biot Savart law has to be replaced by a more challenging equation. Now what you find is that you get a coupling between the electric and magnetic fields. I will not test you on your ability to derive magnetic fields using the Biot Savart law. However, I think it's important that you see me derive some important examples, like the magnetic field of a single wire, a magnetic field of a loop, a magnetic field of a solenoid. And the reason why is that it leads to better understanding of the behavior of the magnetic field. So the process of deriving electric fields using Coulomb's law is very similar to the process of deriving magnetic fields using the Biot Savart Law. Here is a brief summary for electric fields. So, one, we describe how charge is distributed. By the charge element. So how is dq distributed? So typically it's a function of position. Next, we write out mathematically the little dE fields produced by dq. And that typically means that we really determine the displacement. So the displacement vector is really the core of this process here. So when we look at that little dE field, we then write this guy. Right? And then finally, we then integrate over all of the dq contributions at the observation point. So then we finally get our electric field by integrating all of these little dE fields, which then gives you something like this. We have the strength constant, then we have functions that give you something like this. So now we essentially have to repeat the thing with the Biot Savart law. But I need to be really clear about a couple of things. In using the Biot Savart law, we start with a steady current. Which is a continual flow of charges that does not change with time. And what that really means is that is charge is does not accumulate or get destroyed at any one point. Because of this, a line integral is used to evaluate of course, over some path, the contributions of the current to the magnetic field. So that whole statement was about the line integral. Note that when we talked about electric fields, we dealt with fluxes through a surface. Therefore, we had an area integral. So here's the general process. And note that some of these equations I have not described yet. Or some of these stuff that I'm going to write down. This is not the purpose. So here is the general process without defining any terms. This is only to show the similarities in process between electric and magnetic fields. Okay, that's the whole point of this. So I repeat this now, as we did already. So the first thing that we have to do is we need to describe how a constant current is distributed. Like along a line or a loop. Using a current element. Instead of a charge element, we have a current element, which we write as I ds. And that's going to be a function of position. Next, we write out mathematically how a little dB field is produced by a single current element. IDS. And again, the big part of the deal here is that we need to determine the displacement vector. Just as before. So then we're going to write in here is that we're going to have our little dB. There's going to be a strength constant. mu naught divided by that, and then we have I ds cross r hat divided by r squared. You can see that it's an inverse square law, just like electric fields. And then what we do next here is that then we integrate over each current element contributions of each I ds at the observation point P. So if I look at this thing, we then have that B is then going to be the integral of dB. And then we have mu naught 4 pi. And we're integrating this along a line somehow. And we have that. This integral is usually around a closed loop, since stationary currents can only flow around a closed path. However, this law also applies to infinitely long wires too. So I mean, it's a little strange that you can do that, but it turns out that it works out. Now I want to look at the details of this Biot Savart law. So let's look at the details now. And I could see three major points. One, the magnetic field must have a cross product behavior since electric charges circle magnetic field lines and the cross product of the magnetic force. So we expect here that because the magnetic force is IL cross B, that it has to have that magnetic thing. Now, we have to be a little bit careful because we can also look at a single charge. And we could say that we have this guy right here. But remember that the Biot Savart law is about current, not charges. They're not the same. So just to restate what I just said, there must be a current. IL to produce a magnetic field. On the other hand, right, we could say that we have a moving charge QV. But as I said already, they're not the same. This law is about currents, not individual charges. And the other thing here is that we need a displacement vector which means I need magnitude and I need direction, where the fields start as inverse square laws. So without further ado, here we are. So then the Biot Savart law, which is also known as Maxwell's third equation, reads like this. The magnetic field due to a constant current in a conductor, let's say, at an observation point P is this, where I have B is then going to be mu naught over 4 pi, the integral of I ds plus r hat r squared. So just to be careful, because we haven't done this in a while, where r is the magnitude of the displacement vector, r hat is the unit vector in the direction of r, which then leads to our angle theta. And this here is the angle between I ds and r hat. And then we have this strength constant. So we've talked about the strength constant already. And like we said already, this number is really small, but it depends on the units that you use. But this is 10 to the minus 7 Tesla meter per amp. So those are a definition of the terms. So now what we want to do is visualize the magnetic field. To visualize a magnetic field, say in a current carrying wire conductor, one uses I ds plus r hat to get the directions. So let's try to do that. So when I'm looking at this, I'm going to pick a current that's going to go into the board. And this is going to be IDS. That's the direction of the current. So it's going into the board. So now what I'm going to do is I'm going to pick points. Let's say that I pick a point here, 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 here. But I could have also picked points here, and I could have picked points here, here, and here. And here's what I'm seeing. So if I pick a point at 1, okay, so this is my R. And I'm going to say that this is point 1, 2, 3, 4. So as I go around, what you're seeing here is that the vector R keeps changing. So what does that tell me about the magnetic field? So if I look at the magnetic field at point 1, using the right hand, I'm going to have R cross. I'm going to have I cross R. I'm going to get a magnetic field that then points downwards like this. Now remember, let's draw this one more time. So I have the current going like this, which will then be IDS. Then I have my vector going like that. So if I have my index finger in the direction of the current, and then I take my middle finger and I go to the right, that forces me to turn my hand over, which then gives me a magnetic field pointing down like that. So that's the magnetic field right there. Now, if I keep going around, then I'm going to get a magnetic field here by the right-hand rule, magnetic field here by the right-hand rule, and a magnetic field that does this. So what you're seeing here is the magnetic field is doing what? It is rotating around the this current. So if I now take an infinite number of points around the circle, you could imagine that I have something like this. Now, to make this a little bit more symmetric, let me move this over right here because I'm going to need more space. So then if I have a wire right here, and if I start looking at the circling here, you could see here that I'm picking symmetric points. Then I'm going to get a circle that goes like this. It's not a well-drawn circle, but it's a circle nonetheless. And you're seeing here that this guy is rotating around it. So in other words, when I look at the magnetic field, I'm seeing the magnetic field being tangent around the circle that I've just drawn like that. It's not tangent, it's just that at that point we're looking at that. So the B field circles into itself and goes around the wire carrying current. However, magnetic fields are inverse square form. In other words, the magnetic field is 1 over r squared. Graphically, we have to account for this. So if I have a wire, let's say right here, then I could pick point. Let's say that I pick a point right here. Well, if I pick a point here, that's going to have this magnitude of r, and I'm going to say that it's going to produce a field this big right here. And that's because this is proportional to 1 over r squared. Now, if I get close to this, and I pick a point, let's say right here, well, that displacement is now smaller. As a consequence, right here, I should have a larger field. And the reason why this is a larger field is because the displacement is smaller. Or I can have a field that's, let's say, farther away. So if I look at this thing being farther away, then that tells me here that this guy here is going to be large. Therefore, the magnetic field here should be small, and that's because it has a large, distance away. So now if I continue to draw this picture and I look at an infinite number of points, what is it that we actually see here? We see that we're going to have magnetic fields that are going to circle. And as they circle, if they're really close here, you're seeing that the line density is very high. If it's very high, that means that the magnetic field there must be very strong. But as I get farther away, you could see that the line spacing is getting wider. And as I get even farther away, the line spacing gets even farther. So if I start to look at points along this thing, we know that the magnetic field must be going in this direction like that. So I would expect that if I look at the magnetic field in close, that should be a very large magnetic field because the distance is really small. But as I start to go out, you're seeing that the magnetic field is getting smaller and it's getting even smaller. That's what the inverse square law is telling us. Since the current is continuous, a more useful right-hand rule emerges. Called the curl right-hand rule. Now note, I didn't check this on the internet, but that's what I was told when I was a student. So I'm going to use that language. It may be incorrect, but that's what I'm going to call it. So in this case, you take your thumb and you point that in the direction of the current. And then your fingers is they circle around the current. So in this situation, we then say something like this. So the thumb points in the direction of the current where the magnetic field curls around in the direction that our hand is curling. Now, there's some pretty good images from Wikipedia. So let me share these with you. And here they are right here. And you could see that if I have a curl, you're seeing that if I put my thumb in the direction of the current, then I'm going to have the magnetic field circling across the wire. Now, the same thing goes here. Here, they're showing that if I know the direction of the magnetic field, then as I curl my fingers, that's going to be the direction of the current. But they're really one and the same. Or you could take your hand and put your thumb in the direction of the current, and you get the same direction there. Now, one of the things that also is on Wikipedia, which I really enjoyed seeing here, is that this right here is a Swiss 200 franc banknote. And look at that. It has the right-hand rule. How cool is that? Really awesome. Now, let's make some remarks to just finish this off here. The first thing here is we said that the Biot Savart is Maxwell's third equation. So that means it has to look something like this. So in integral form, which is what we typically deal with in this course, we're integrating around a loop or a path, and it looks like this. But we spent time in trying to interpret the geometry of the derivatives, the three-dimensional derivatives. So in differential form, it looks like del cross B, which is in mu naught times J. And so in differential form, it looks like that. But we're not done with this equation. When we add electromagnetic induction, this equation is going to change. And you're going to see that in special circumstances, there's a new term that comes in, which is now including the time rate derivative of the electric field. So in chapter 10, we will add that term to the Biot Savart law. Second of all, one cannot verify the Biot Savart Law directly, since one can never isolate a current segment experimentally. I can't look at a single piece of current. What is measured is the net magnetic field, and experiments have verified these very well. Three, always be alert to using symmetry to simplify calculations. That means try to reduce one of the terms to a single one instead of, let's say, a whole line or a full circle, whatever. And then finally, I would say that there's a misleading statement about the Biot Savart law, and we should probably talk about this a little bit. There are a number of textbooks that claim that the Biot or Biot Savart law can be written as either the way we've been writing it, which is, let's say, r squared, but if the current is constant, we can then pull out that guy. So we're really integrating this guy right here. And once again, you're seeing here is that we're talking about a constant current. And textbooks will also write that the Biot Savart law can also be written like this. This is a misleading statement. It only applies to steady currents and a point charge moving in space does not constitute a steady current. The Biot Savart was published in 1820, and Heaviside in 1890 approximated the magnetic field for V much, much less than C to be equals to mu naught over 4 pi QV cross R squared. So it's an approximation. It's not the full magnetic field. Heaviside is huge in electromagnetism. He's the one who effectively wrote down what we now call Maxwell's equations. So lastly, I will apply this law to two important examples. One, we have a straight current carrying conductor, and the other important one is a circular current loop. There are other examples, but we could use both of those in that sense.